ligand group orbitals are of lower energy than the metal T2G orbitals. Therefore, bonding molecular orbital have the character of ligand group orbitals and the anti-bonding molecular orbital have the character of metal T2G orbital. Therefore, the electrons supplied by the ligand's T2G orbital will fill the pi bonding molecular orbital, and the electron from metal T2G orbital will fill the pi anti-bonding orbitals. The Eg star orbital are not affected by sigma pi bonding, and T2G metal orbital become anti-bonding and hence are raised closer in energy to the metal Eg star anti-bonding molecular orbital. Thus the energy difference delta zero between T2G star and Eg star decrease relative to the difference where metal ligand pi bonding does not exist. The lower delta zero is smaller for OH minus ligand compared to water because OH minus is better pi donor. T2G pi, T2G, T2G, T2G star pi star, EG star sigma star. If the T2G ligand orbital are empty and of higher energy, then the metal partly fill T2G orbital, then ligand T2G orbital overlap with metal T2G orbitals to give bonding and anti-bonding molecular orbital. The ligands having empty T2G orbitals of the little higher energy than that of free metal cations are R3P, R3AS, R2S with vacant d orbital and carbon monoxide, carbon cyanide, NO plus, phen, N2 with vacant pi star orbital, etc. Of course, this ligand with vacant pi star orbital also have filled pi orbital and can function as pi donor. But because of very low energy, this orbital cannot overlap with the metal d orbital. These ligands with empty T2G orbital are called sigma acceptor ligand. Since the ligand group orbitals have higher energy than that of metals, d orbital therefore bonding molecular orbital have the character of metal d orbitals and anti-bonding molecular orbitals have the character of ligand group orbitals. The resulting bonding orbitals are delocalized over both metal and ligand, which were the non-bonding and localized on metal in the absence of pi bonding. Since the bonding molecular which have the character of metal d orbitals are decreased in energy as compared to T2G orbitals in absence of pi bonding. Therefore, energy difference delta zero between T2G bonding and Eg star anti-bonding orbital is increased relative to the difference where ML pi bonding does not exist. The energy of T2G star orbital is also higher than that of Eg star orbital. Therefore, electron from metal d orbital fill first in T2G and then in Eg star orbital. T2G pi, Eg star sigma star, T2G star sigma pi star. The ligand field theory explains the order of ligand in spectrochemical series from weaker to stronger when pi bonding is significant. It has been observed that ligands such as halide, sulfur 2 thiourea, which are stronger pi donor decrease delta zero, and pi acceptor ligand like carbon monoxide, carbon cyanide, R3P, NO2 minus, etc., which are strong pi acceptor increase delta zero relative to the delta zero where there is no pi bonding. Therefore, the strong pi donor ligand are at the weak end, and the ligand which are strong pi acceptor lie at the strong end of the spectrochemical series. The ligand having little or no pi bonding ability have intermediate value of sigma of delta zero lie in the middle of the spectrochemical series. Thus, it has been concluded that the value of delta zero increase in order of pi donor smaller than weak pi donor smaller than neither pi donor or pi acceptor or smaller than pi acceptor or smaller than strong pi acceptor. Iodine minus smaller than bromine minus, smaller than chloride minus are strong pi donor. Then chloride minus stronger, smaller than fluoride, fluoride minus smaller than OH minus, smaller than O2 minus is weak pi donor. Then O2 minus smaller than H2O, smaller than pyridine, smaller than ammonia, smaller than ethylene diamine, which is non-pi effect, smaller than bipyridine, phene, weak pi acceptor, smaller than NO2 minus, smaller than phosphorphosphine, so phosphorphosphine, smaller than CH3 minus methyl hydrogen anion, smaller than cyanide ion, carbon monoxide. These are strong pi acceptor except methyl and hydrogen minus. In the spectrochemical series, the ligand CH3 minus and H minus ligand are neither pi donor nor strong pi acceptors, yet they are very high in spectrochemical series. The reason is that these are strong sigma donor. Sigma bonding in tetrahedral complex. The procedure for constitution of molecular orbital diagram for tetrahedral square planar complex is same as that applied for octahedral complex. The metal atoms or iron in each case use is it. Same 9 valence orbital available for bonding, but their symmetry properties are different for each geometry. For a tetrahedral Ml4 complex and metal, S and p orbitals have A1 and T2 symmetry respectively. The dxy, dyz and dzx orbitals have T2 and d square y square dz square orbital have asymmetry. It is seen that the symmetry of p orbitals and that of dx, y, dy, z, dzx orbital are identical, that is due to symmetry. It is due to the fact that the p orbital hybridizes with s orbital, sp3 hybridization, and dxy, dyz and dzx orbital hybridize with s orbital. sd3 hybridization form tetrahedral geometry of the four ligands group orbital. Ligand group orbital constructed from ligand lone pair orbital 1 have A1 and the 3 have T2. Symmetry. A1 orbital ligand group orbital interact with A1 orbital of metal to give one bonding and one anti-bonding molecular orbital, and T2 ligand group orbital. For tetrahedral Ml4 complex, the metal s and p orbital have A1 T2 symmetry respectively. The dxy, dyz and dzx orbital have T2 and dx square y square, and dzx orbital have asymmetry. It is seen that symmetry of p orbitals and that of dxy, dyz and dzx orbital are identical. That is T2 symmetry. It is due to the fact that the p orbital hybridizes with s orbital sp3 hybridization and dxy, dyz and dzx orbital hybridize with s orbital. sd3 hybridizations form tetrahedral geometry of the four ligand group orbital. LGO constructed from ligand lone pair orbital 1 have A1 and the 3 have T2 symmetry. The A1 orbital ligand group orbital interact with A1 orbital of metal to give one bonding and one anti-bonding metal orbital, and T2 ligand group orbital can interact with both sets of T2 orbitals of metal P and dxy, dyz, dzx to give one bonding and two anti-bonding molecular orbital. Figure 4.25. In contrast to the octahedral complex, the metal e orbitals are non-bonding. The separation between the e and the next higher T2 molecular orbital is equal to delta T as in crystal field theory CFT. For a complex such as cobalt tetrachloride 2 minus, there are total 15 valence electrons, of which 8 electrons produced by 4 ligand. The 2 electrons per ligand and the copper 2 plus D7 ion furnish 7 electrons. 8 electrons are filled in the bonding molecular orbital A1 and T2. 4 electron in non-bonding electroorbitals and 3 in the slightly antibonding T2 orbitals. Ml4 A1 T2 E T2 star A1 star T2 star. T2 is T2 A1, E is E T2, T2 star is N plus 1 S A1, T2 star N plus 1 P T2. Sigma bonding in square planar complex. In square planar complex, the d orbital have A1G d square 2 EG dyz dzx B2G dxy and B1G dx square y square symmetries. The p orbital have A2U pz and EU pxy dx symmetry. The four ligands lying along the x and y axis give rise to ligand groups orbital of A1G and B1G and EU symmetries. These ligand groups orbital interact with meta orbital of same symmetry sigma molecular orbital as shown in figure 4.26. The A1G ligand group orbital interact with the both A1G metal orbital to form one bonding A1G and one slightly anti-bonding and one anti-bonding molecular orbital. The metal orbital B2G, EG and T2U remain non-bonding because they have no symmetry similar to ligand groups orbitals. In general, the square complex are formed by the metal ions like nickel 2 plus with strong ligand like Cn minus, Pd2 and platinum 2 minus ions. There are 16 valence electron, 8 from the 4 ligand and 8 from the metal ion. The 8 electron from ligand occupy the bonding molecular orbital A1G, B1G and EU, and 8 electron from the metal ion occupy B2G, EG and A1G, slightly antibonding molecular orbital, and the complex are diamagnetic. The square planar complex are highly stable though they contain 16 valence electrons. This is due to the reason that all the bonding molecular orbitals are filled and the antibonding molecular orbitals are empty. Adding additional electron would destabilize the complex because the additional electron would enter into antibonding molecular orbital and lower the bond order. The complex containing electron less than 16 are also less stable because they have lesser number of electrons in bonding molecular orbital and lower the bond orders. A1G, B1G, EU, B2G, EG, A1G, B1G star, E2U, A1G star, EU star. In right hand side A1G, B1G, EU, and in left hand side EG, A1G, B1G, B2G. In left hand side of A1G level N plus 1 as A1G and in A2U N plus 1 P A2U EU. Crystal field splitting diagrams for trigonal bipyramidal, square pyramidal and pentagonal bipyramidal complex. Energy dxz, dyz, dxy, dx square, y square, dz square. B dxz, dyz, dxy, dz square, dx square, y square. Dxz, dyz, dxy, dx square, y square, dz square. So this A is a crystal field splitting diagram of trigonal bipyramidal. Then B is crystal field splitting diagram of square pyramidal, and the C is crystal field splitting diagram of pentagonal bipyramidal complex.